Yeah, start the recording for people who are not here in real time. Let me say, wow, this, so we have a shorter week this week. What we have decided to do, as you will see in a moment, is to compress the week, a bit of the content from both classification and neural networks and fit it in essentially 1.5 weeks. So today we'll talk about part of classification, as we will see in a minute. The motivation comment for today, I guess the point is choosing both the input and the classes are important. Of all the data points, you could possibly say that, well, there's a separating line that separates stuff I like versus stuff I don't like, or maybe it separates here. Or maybe the separation should be somewhere here, depending on who you are, right? So our taste for fruits or things that may or may not be considered fruits are quite personalized. For example, for me in person, personally, I feel like, okay, here's the curvy hyperplane enclosing the stuff that I like. Right? How do we represent that? There's a thing called one-class SVM, which we may or may not have time to see this semester, but we will be talking about classification. So, okay, more seriously, in today's lecture, we are going to start by defining classification problems and take a quick glimpse of decision theory as it's covered in chapter 1. Followed by some philosophical discussion about what the components of a supervised machine learning system is like. I feel this is the right week to do this philosophizing because before that you haven't seen enough of supervised classification, and then this the content of the classification chapter provides ample material to think about the different components. We'll then talk about 3 different views of classification, how to learn a good classification. The first view is called discriminant functions. The second view is generative models. The third view is discriminative models. Along the way, so the blue is what I felt like Easter eggs that comes in on the side of the technical discussion. The first one is a scenario where least squares doesn't work. The second one is where do the logistic function come from? Because logistic function is quite ubiquitous in machine learning practice these days. We have heard about, most of you might have heard about logistic regression, and they are components of neural networks. So what are they? Where do they come from? And then how things connect to this historical algorithm called perceptron. We can discuss its pros and cons and why it's important. So roughly speaking, I plan to cover, the first few things up to the beginning of generative model today. Hopefully we'll get there. And then on Monday, in week 4, we're going to continue with the heavy lifting in generative models and logistic regression, plus a portion of the neural network content. All right, so let's dive in. First of all, what is classification? So far, the examples you've seen are regressions and regressions on sinusoids as informative examples. So the goal of classification is given some input data, assign it to one of k discrete buckets or classes. Often the definition of the classes come from domain knowledge. And for example, in this slide, some plant biologist says, oh, there are 3 types of iris flowers. Can you classify them based on pictures or some measurements taken on different flowers? So some biologists actually went and measured the let's say, a number of attributes for a number of flowers. Each dot here is a flower being measured. And then we can put them on a 2D plane. The original data set, this is called the iris data set. It's quite famous in the open UCI data repository. It's widely available. It's quite small. Yeah, lots of classes use it, and it's a great tool, sort of data set to test the waters for classification tasks. It has, the original data set has more attributes, but here we're just visualizing 2. I don't actually know which axis is which. We can maybe make some guesses. For example, the petal length. So the 2 attributes are length of petal in centimeters versus length of sepals. And this Wikipedia picture tells you what is the petal, what is the sepal. It's not clear which one is longer, actually. Right, so make our guesses. You can actually load the data set and plot it yourself. So turns out that in this 2D space, there is some separation for these 3 different types of flowers that are colored by different kind of dots. The red dot, I don't know which one it is, which class it is actually, are significantly shorter by one of these measures, either petal length or sepal length. So you can imagine, oh, the space may be divided into 3 regions, such as this might be one class and this might be one class. Although you can also say, what about all the blank space where no flowers exist? So should the class label be undefined, or should it be just blue? Which is open questions, right? Equivalently, so we aim to learn a function that map each point in the input space to a category label, or say don't know, right? So that's basically the kind of problem that classification addresses. Of course, it generalized to much more than sorting flowers. This is really a toy example. You could think about many examples in daily life, from medical diagnosis to automated decisions in, say, financial decisions, in giving people credit of loans, admission decisions in university, if it's sorted by machine learning algorithm, hopefully not completely at this point, and so on and so forth, right? And classifying images, classifying documents, and so on. So let's start by representing the task. So far, we haven't had to do this because in regression tasks, our targets are real numbers, and we assume we learn a function whose output are real numbers or a vector of real numbers. If the classes are binary, which are the simplest case, and we shall focus most of our efforts discussing this because of the reductionist principle. If we can do binary, we can probably use the same insights to do multi-class most of the time, as we will see. If the classes is binary, we represent it with one single target variable that takes the value 0 or 1. So this can be whether we're meeting in person or remote, whether student pass or fail class, whether something in medical imaging is benign or malignant, or whether a customer should be given credit, right? Yes, no decisions. Either or decisions, right? So what if we have many classes, which also happens a lot? So one of the preferred representation currently in practice is what's called one-hot encoding. That's the name. It's called one-hot because now we represent the K classes as a K-dimensional vector, right? And then we assume only one of these classes is active, meaning so the entry corresponding to that class is 1, everything else being 0, right? So the corollary of that, if we sum over the different dimensions of T over I from 1 to K, it should be 1, right? And then Ti is binary. So this applies to the iris flowers we just saw. It applies to certain object classes, only like a photo can contain both a cat and a car. That would have been called multi-hot encoding in neural network lingo. And it applies to, say, natural language models where, for example, we are asking the model to generate a sentence and we're spelling out one word at a time. Right. So let me also say that these two representations are very useful and they help us get started, but they are by no means the only or the best representation for a task. For example, if we have time series or sequences, we might need a sequence of these labels. We might have a graph where there's a more complex structure. In section 4.1.5, we won't go through this, but if you are interested, you can see there is a derivation inside the section of the book that essentially connects what's called Fisher's discriminant to least squares by essentially tweaking the output representation from binary to a real value, which is very neat. And then in section 4.1.7 and the kernel machine section, the alternative representation is the class label is +1 or -1. This is convenient in certain cases. Right. So now that we have defined what the learning task is, and as usual, we for now assume we have input, which is called x, which is a vector. What does classification or making decisions really mean? Right. So as the book spells out, the decision theory is the science of taking a specific action based on our understanding of the value of the target is likely to take. Right. So slightly more formally stated, we would like to estimate the probability of a target, right? So there's a change of notation inside the textbook within the space of a page. So it starts by talking about the target, but in here, the target is represented as one of K classes, shorthanded as curly C sub K, right? So we're interested in estimating probability of the class given the data, or in other words, represented as this using Bayes rule class like data likelihood given class. Or you can think of it as the joint probability between class label and input and data point X. So these are all interchangeable representations. And the book says that we shall see that the decision stage is generally very simple or even trivial once we have solved the inference problem. So the inference problem is basically estimating one or more of these probabilities, right? And it says, well, if we're going to decide, say, whether we're meeting remotely or in person based on like people's scheduling, we just need to estimate this probability and it's trivial. If we're deciding, say, pass, fail, say for a particular student for a particular class, hopefully at that point we have gathered data about like the performance across all the assessments, and the decision should be trivial after we aggregated the available evidence. So that applies to a lot of scenarios. Again, I would say, especially in this day and time, more than 10 years after the book is written. I think about 15 years after the book was first published. One needs to pay more attention to the distinction between estimation or inference and decision making in general. This is because I feel when the book was written, machine learning was, as a field, has been evolving, but the systematic view of it was still new. And being able to do the inference or estimation is a big deal. And now that we have, the field in general has been doing it for 15 years more, there is better perspective on it. And there is better perspective certainly about how it connects to other different fields, such as operations research. And the field, there is an entire field called decision theory, right? Just to give people a number of counterexamples. So if we are going to, let's say a patient shows up in the hospital who is fairly sick, and the doctor have multiple medical tests at their disposal to figure out what, basically what is going on. And the different medical tests may have different sensitivity and cost and wait time. So considering all of that, which test should the person take first, and based on that decision, whether or not to give the patient a second or third test is, I mean, there are many interesting estimation and inference problems in there, but the decision is far from trivial, right? Another example that's closer to the situation right now is, for example, if you're a mayor of a big city, and you wanted to, or the public health official of a city, and you wanted to design a policy of people going to testing and whether they subsequently quarantine themselves, or maybe some people who should go to quarantine without testing themselves. So what is the best public health decision there? There is a large number of variables, right? So for people who have close contacts with, say, a number of active cases, they probably already carry the vaccine. The right decision is probably not to test and just quarantine them. Or for people who flew in from an international flight, the current decision is go to quarantine and yes, we'll test you, right? What if your testing capacity is actually constrained? What if we don't have enough tests for susceptible people, which was the case at the beginning of the pandemic last year? So all of these decisions are very complex. We would say machine learning can help, but it's certainly not the answer to the big picture. This area of basically decisions and estimation, when they interact, it represents some of the frontiers of both theoretical and practical machine learning, such as what's called active learning, online learning bandits. The way, an area where they integrate the most closely is actually reinforcement learning, which is very cool. And then there is intersection of machine learning and economics. So this is more of a culture rant, right? But I feel perspectives are important. A bit more later. So let's get to the right. Grids of the tiny part of decision theory that we're going to cover. So one view is that we would like to make decisions such that the errors are minimized, right? So on the right of the screen is a schematic of what some of the probabilistic quantities we're concerned with, such as the joint probability of the data in a class. So P of X and C1 is bimodal here, and P of X and C2 is sort of unimodal and Gaussian-like. So what will be our best decision? Here, the input X is one-dimensional. If we can, the decision essentially is by bucketing the space of input X into different regions. Let's say call like region 1 as the region corresponding to class C1, and region 2 is corresponding to C2, and so on. Note that the C1 and C2, like the region 1 and 2, need not be contiguous. You could have, in theory, like R2 at the far left-hand end of the axis as well. But I guess you get the idea. So if we cut, let's say, the region at the point x hat, we can essentially compute the probability of error by looking at essentially what is the probability of x belonging to the other class, say R1, given, well, x, but x actually was belonging to C2. So if we look inside the region R1 and then look at the probability that x actually belongs to C2, you can see that it's this part, right? The combination of the red and green part, right? And then what is the error from the other class? Basically, x in region 2, but it's actually belonging to class 1. So that will be this blue part, right? Written in integral form, basically integrating over the potentially high-dimensional regions of R1 and R2, the probability of error in the respective regions is just probability of x belonging to the other class, or all the other classes if we're dealing with multi-class situations, right? So equivalently, we could, right, so like 1 minus probability of error mistake should be probability of it being correct. So we wanted to basically maximize the probability of being correct. In this case, it's just 1 minus these in each of these terms, right? 1 minus the joint probability of data and class, right? Oh, by the way, if you have downloaded the slide earlier today, then download again. I posted an update just before, about 20 minutes before the lecture. But right, so move on. So what are the potential problems that we will encounter for minimizing classification error? All right, so there is a question. So let me do the following. So why don't the class think about this, right? And right, Noah Hinton's question is basically what is P of X? Let's see if I have some, yes, I have some space to write here. So I'll just write on the last slide. So good question. The answer to this question is, this is a shorthand of the random variables are X and class label C. And then P of X curly C1 is a shorthand of P of X equals the point, right, I should have a different symbol. Let's say some bold X equals the current value X, and then the class label C equals to the current class label curly C1. And the first, in this picture, the first random variable is continuous, and then this one is discrete. Yeah, you might say, yeah, but we traditionally talk about either discrete probability distributions or continuous PDFs. What is this beast mixing the two? What it actually is actually it consists of, I like to think of it as basically two slices. They are overlapped on this picture. What I wanted to what I find helpful is to think about there is the axis C, there is the axis X. In axis C, there are actually just two values. So therefore, the PDF is, or the PDF equivalent of this thing is actually, this is C2, this is C1. C2 is a unimodal thing, C1 is a sort of a like bimodal thing. And this is the joint probability distribution. So it's sort of two continuous PDFs. They are just sliced. Rather than being in 3D where we have a mountain, in here we just have two paper mountains being the two, joint. I hope that helps. Shout out if no, if it's still confusing, but let's move on. So would anyone want to chime in about like one potential pitfall for minimizing classification error? I had a hint on the screen, but you don't have to follow that. No, people are shy. Oh, okay, yes. Noel said asymmetrical outcomes. There's another thought about overfitting. Yeah, let me start from this like class asymmetry. I think both of my okay, Ella said false positive. Yeah, let's say we break down these terms to see what they really mean. The two aspects, so there are many different things to consider. I would say the two aspects I would like to emphasize, at least in this lecture, I summarize them as class asymmetry. Right. And I break it down into two ways. The example goes as follows. So suppose we have your data scientist helping to analyze some genetic disease. Right. Among the patients who come to the clinic, okay, 99.9 of the patients, they're fine. And 0.01, 0.1% of the patients, they have the problematic gene, right? So what happens if we just brute force, like minimize the classification or classification error in the whole population? So the right decision seemed to be then, or the quote unquote, like if we minimize classification error, it would seem like we should just label everybody as fine. Then our accuracy is at least 99.9%. So I would say this, I will call this class imbalance. And the second consideration here is related to what Ella posted on the chat. So there can be different costs to make different kinds of errors. So, for example, if the decision and actual state of the patient is fine, okay, like not fine. Right. So if the decision and the actual situation actually agrees, let's say we don't care about this at the moment, and then if a patient is actually fine and the you flagged them as not fine, there will be a psychological cost, but you can put the patients through subsequent tests and monitor them, right? And then the cost is probably, the overall cost is probably lower than the other way around. If the patient is actually not fine, you miss them, then the cost is cost of life, right? Let me just informally say this is lower than the other error, right? So it's asymmetric costs, right? Costs of error are different across different classes. Therefore, just minimizing the whole classification error over different data points does not make sense in some cases, right? So let's look at some of the remedies for the brute force minimizing of classification error. So the remedies for the two things we mentioned is minimize loss instead, right? So there is this equation 1.80 and 1.81. It basically says if we have a loss matrix for different classes, such as this one on screen, which is essentially like what we drew, but with real numbers in them. If we classify a cancer patient as normal, the cost is 1,000. Well, it's hard to put a number on, say, cost of life, right? It's a very hard thing to do, and sort of a debatable thing to do. On the other hand, this is how places like insurance and like, for example, doctor's liability operates. And in a sense, it is also how a lot of sub areas of economics operates. They say, oh, assume these things all have a cost and they are quantifiable through some abstract common currency. I've been reading a fair bit of COVID-19 papers recently that was how economics operate. I'm not saying this is a best model, but it's yeah, it has powered many things that we experience right now. So if we subscribe to this this one way to operationalize cost, then instead of minimizing error as in the last page, we can essentially minimize weighted loss, right? So the second term is, as we were seeing, it's the joint probability of data and classes, and the first term is basically this loss entry. Just pick out the corresponding loss entry, right, and plug in here. The decision then is by, for each data point, take the minimum loss, right? That makes sense. The second recipe we're going to talk about is balanced metric. Basically, instead of this minimum error rate over all data points, we could say, now, assume we have two classes, say positive, and we label them right. We label them as positive and negative, right? And then we could devise balance errors such as by calculating the fraction of correctly classified data points in the positive class. So in true positive, so this is truth, this is your ML like classifier, right? When the true class is positive and the classifier also thinks it's positive, it's considered a true positive, right? So what I'm drawing here is commonly called a confusion matrix in machine learning practice. It's a very useful thing. I don't know why. I don't see it in the textbook. It might show up somewhere else, but it's useful. So if the true class label is negative and I classify as negative, then it's true negative, right? And so in these other cells are false negative and false positive. So you can see, because we've talked about discrete probability tables, you can basically, so the true positive and true negative, they are counts over a, say, test data set. And they should normalize to, like, they should marginalize to the true number of positives and negatives, or the fraction of decided positives and negatives on the over the columns. So what this balance accuracy metric says is that we can just count the fraction of correct decisions for both the positive and negative class, and then average them. So that's simple. This is from this paper downstairs cited here. It's, well, within the last 10 years, more or less, and written by Qing Song, who used to teach this class, and he co-wrote the textbook that you guys in IML used, right? And just this morning, I messaged him and said, look, your proposal for balanced classes are actually getting lots of attention in academic literature only in the past 2 years. Why is it? Part of the reason that is this metric is so simple and it's easy to compute. It quite solves lots of problems. So that's nice to see. A good example of a simple idea that's very useful. I would basically footnote this by saying, I chose this metric also because it's the metric, or one of the few metrics that I can cover within the space of 1 or 2 minutes. There are many other possible metrics that aim to address the class or cost imbalance problem, all the way including what's called precision recall curve, RC curve. If you have touched search engines or retrieval problems or recommender system problems, you can look at top K accuracy, basically how many things are relevant within the top 10 blue links that Google are giving you. There's something called mean average precision and so on. We're not going to be able to get through it. So hopefully lectures like this will also allow you to read up on new metrics and critically think about them before adopting them. Right. The last point that I would like to cover from the decision theory section is that the machine shouldn't be forced to make a decision. Like it can and should work with downstream humans. One of the ways to do that is to have a reject option, right? For example, if we look at the class posterior, well, we can say in the middle section here, it's really ambiguous. Maybe we just decide on the two sides, and then in the middle, say, collect some more data or get a human to look at it. This happens all the time. In fact, the recent approach from Stanford that claims to diagnose skin cancer more than dermatologists is actually working with dermatologists when they're deployed. And sometimes they review features that the dermatologist might have missed. Sometimes they the dermatologist will know more, that the task of dermatology is very different. Rather than just looking at the picture and say cancer or not, they are looking at the patient holistically and figuring out what the best way forward is. Back to the note about decision theory. Okay, so for this class, we're going to park the complexities again. So the beauty of, I guess, math or machine learning methods is that we try and reduce the problem to a simple form and address it in sensible ways. So remember our basically toy distribution of 2 mode versus 1 mode in 2 classes. We could tackle this using 3 different approaches in broad strokes. The first one is called finding a discriminant function, f of x, which essentially separates these classes, right? In 1D, there's not much of an f of x because if the class regions are continuous, we're just right? We're just picking a point to split. Although discriminant function, we can also think of it as finding the split point between classes, right? The second type of model we will talk about, and also the sequence of the book, is actually what's called generative models. So it says instead of just targeting an f of x, let's try and estimate p of x given class label. And then assume we can get the class prior from somewhere, then from Bayes' rule we can find the posterior. Right, so you might notice there are several different notations being sort of almost interchangeably used here. So in the decision, deciding which class it is, so we wanted to essentially find a class that has the maximum posterior probability, argmax over k, probability of the class small k given x. But in this picture and many other places, we find ourselves doing, let's say, argmax over k of the joint probability between feature and class label. Right? Yeah, so what's going on here? The reason is Bayes' rule basically allows us to rewrite this as p of x and p of ck given x. So for the same input point, p of x is the same for different classes. Therefore, this term kind of cancels out. And then these two criteria becomes equivalent. Right? And then, so from what we just said, alternatively or equivalently, we could model the joint distribution between x and ck directly, and it's also a fine generative model. And then we can use decision theory to assign each new x and observed data point to one of the classes. So the book discusses whether it is sort of necessary to go through all of this trouble to estimate these probabilities if we could just learn the discriminant function. Turns out there's also a third possibility, which is just have a model or parametric form for the posterior probability directly and try and estimate that. Once we have that, we can just directly use this. Assume this is f of x now, then we can using fx to assign each new x to a class. Right, so there are pros and cons about these different approaches, and we'll go through them and we'll have a critique as we go along, right? So here's an example that the book provided about whether or not it is like the relative merits of generative versus discriminative, or how much probabilistic information we need. So this is essentially a scaled view of the 2-mode versus 1-mode classification task we were looking at. So here it's scaled by class prior. We can see the blue class here is less prominent. If we estimate the class conditional data distribution, what we get is, well, we need some more, like essentially data and the statistical power, loosely spoken, to estimate this 2-mode distribution and the red 1-mode distribution. On the other hand, if we estimate the posterior of class, turns out that the posterior is not bimodal. As long as we know sort of the blue curve is larger than the red curve to the left of 0.5 something, then we seem to be fine, right? So it is a modeling decision deciding which quantity to model. So I'm just gonna pause for a philosophical point about all of the stuff we just discussed. So far, we have discussed different components of machine learning, but we have not really called them out. And let's try and attempt to do this. So I would say that the lecture slides from last year has a slide that's somewhat like that, but not in graphical form. It's a list of bullet lists. Let's see how we go with this one. So let's say there is the real world. Here's my poor drawing of a globe, right? Let's say. From which we deduce what we call data, D, let's say. Right? And it consists of, let's say, sets of xi's and sets of yi's in regression or classification, right? And inside this is someone would have spelled out the task for machine learning, and then there is the input to the task, right? And in this class, we are assuming that we start from data points and this arrow has been done for us. But in reality, it's quite controversial and there's lots of important decisions. So for example, what Amazon and online shopping website uses as X and Y are essentially our behavior exhausts, what we click and so on. If you're the government, you'll be asking about like privacy questions on what goes into this arrow, what can be part of the input, what cannot, right? And then, what we do is we define some function f of x parameterized by some w. Oh, let's see, just f of some variable parameterized by w. So here's another thing: it's that the word model is very loosely and imprecisely used, and it's very overloaded. In the narrower sense, I would call basically this particular function that represent that we're trying to learn as the model, what form it is, whether it has any structure, and so on. And then to assume we have such a function, we can choose like a loss function or objective function. Let's say we call it loss L of the W vector, right? And then the next step is what I call learning. When we learn, we essentially say find W star that is the best W in some sense, such as the maximum likelihood we've been talking about, or maximum posterior, or find some posterior distribution of W given the data set, right? And prior, as in the Bayesian view. Okay, this is all fine. I put two words in quotes because they are very loaded, I would say. In the narrow sense, model and learning is here, and we'll see a bit more about. And then what happens after we quote unquote learn a model? Let's see, green pen is that we the real world didn't just give us data for learning and training. For some new data d prime, that we only have the input, let's say x of j, for range of j's, and we don't have the output with us, which we do what we call prediction, which is also overloaded word because it's not strictly sort of prediction in a temporal sense, or prediction, for example, predict when the apocalypse will happen for the world. That's not that. So let's say one value approach is take the W star we learned and then just check it through the F function, right? So that's most of what your code will do. You may say then, well, we wanted to know how well we have learned, right? So there is evaluation metric, evaluation involved, right? The metric can be like error, sum loss function, and many other things, right? And you may say, well, if you are the machine learning engineer, you did stuff on this slide, and now you want to ship it to, say, the actual production system, right? And then the users will want to interpret or diagnose your model as it's in use, right? For example, if you train the recommender system for movies, and then during Christmas, people's movie watching habits suddenly sort of shifted. A, people watch more, they have more free time, and B, there is a certain type of, let's say, Christmas movie that people like to watch more, right? So your model may have drifted. So if you deploy your model, the monitoring and diagnosis, your model is nonstop. And moreover, what's not in this picture, sorry. Yeah, okay, my screen share has gone. Let me bring it back up. Yes, please, start. Yep, okay, here's it. So in reality, all of this is implemented like implementation. So let's say like it could be Python, R, like your favorite learning package, Colab with GPUs, TPUs, and so on and so forth. Right. So you might say this is the modular view. In reality, your like loss function and evaluation ideally should help each other. They should sort of either be exactly the same or have the same intuitions. Otherwise, you will be tweaking towards different objectives. And then when you learn, so there is also a middle ground between learning and, well, essentially training and testing. As some of you know, so there is a role for validation data sets, which is a part of the training set, but then you reserve it to essentially make important decisions that is not, strictly speaking, not part of the optimization that gives you the optimal parameter. So in the broad sense, like, so these terms are really misused, I would say. Like in practice, some people will say your Python Pico file that stores the model parameters as the model, right? Or some people will loosely call this whole thing down the bottom as, say, the model. And learning is also, yeah, whether like learning, deciding on the hyperparameters is learning or not. So when we talk about these terms, we need to be precise. I would say there is no one single best way to do this. And then in terms of like the whole machine learning system, I think there are two takeaways I would like to leave this slide with. The first one is there is separation of concerns, right? In the what we call the training pipeline. Basically, if your model is not working, you should be asking whether you should be redefining your model, choose a different loss function, or choose a different optimization algorithm. Or something like that, right? Or whether to go back and examine your data set to see if the distributions of X and Y are strange in a way. That happens a lot. The second one is that if you're trying to do this in a research project or real-world project, what the end use should inform all of the upstream decisions. Okay. So that's that. What we talked about so far is the intro part. It looks like we will need the next half an hour as well. I would rather give it justice than rush, and hopefully those of you who feel you know this already can fast forward. So let's talk about among the three different classes of classification functions. Let's talk about discriminant function first. A discriminant is a function that maps from an input vector x to one of the k classes, where the k classes are still denoted by c sub k. Let's consider two classes to not confuse ourselves before we get any real insight. And let's assume, because it's two classes, we can imagine that we only need to learn one discriminant function to separate class 1 from class 0. And there are two parameters. One is the wave vector w. The second one is called the bias or threshold vector w0. So you may say we've been traditionally just absorbing the bias vector into the feature input by adding a constant input. So yes, we can still do this, but just bear with this for a few minutes, because it's singling out the bias gives us additional geometric intuitions. So here's a picture of the simple linear discriminant, right? If we do W transpose X plus W0, here is the what contours of Y looks like for different values of W. For example, if W is 1 and 2, then the contours of Y is, of course, lines on the 2D plane. If W is the same thing but sign flipped, then the contours are like same, but the direction of the high and low direction are just flipped, right? So the decision boundary between of the two classes is y of x is equal 0. We don't have to choose y of x equals 0, but that's sort of a natural choice. It's certainly not the only choice. And it's a plane of d minus 1 dimensions when the input is in a d-dimensional space, hyperplane, right? So the intuition here is the wave vector w. So if we don't consider the bias term in the same package, the wave vector is basically perpendicular to the decision surface, right? So this it says it's perpendicular. So so assume there are two, let's say, two data points xa and xb on the boundary, on the decision surface, which means y of xa and y of xb are both zeros. And the vector on the decision surface will be, say, xa minus xb, right? So if we take the difference of that and group the terms, we essentially have, because the both of these terms are zeros, the difference of them is also 0. So therefore, w as a vector is perpendicular to the vector difference of vector of xa and xb, because that's how orthogonal vectors are defined. When two vectors are orthogonal, only if and only if the inner product of them is 0, right? So as we said, contour lines are hyperplane, and then y of x in here. So let's say these are lines of y of x equals to 0. then when y of x is non-zero, it signifies the sign distance of point x. So this is some arbitrary y of x, sign distance of x from the hyperplane, right? So let's elaborate on that. I guess this is the slightly more involved page for linear discriminants. So on the left, we have the same function we've been looking at. And so the red line is now y of x equals to 0, or it's essentially, right? And for an arbitrary x denoted by the blue arrow, we argue that, right, so this distance to the decision hyperplane is y of x, right? So the way to derive this is as above. Let's break it down a bit. So we know we wanted to compute the distance, right? Basically, the length of this dashed line. We don't know what it is. So therefore, let's call it r for now, right? Right, and then from geometry or algebra, well, the 2D geometry, we can see we can basically plug in r into the original function, discriminant function. We decompose x into two parts. The first part is so-called x, say, the projection of x onto the hyperplane, or x perpendicular, which is this part. It's the vector sum of x perpendicular with r, right? And we assume that the length of, like, these metrics are normalized by length of w, right? Moreover, the picture from the last page actually says, right, so the magnitude of w actually don't matter, right? So if we multiply w by 2 here, the contours are kind of the same, right? So we expand this expression and make use of the fact that the inner product of w and x perpendicular, this component should be 0 because of what we just covered in the last page, or it should be 0 plus including the bias term. Then we're just left with one term. Basically, it says y of x equals r times w, and the r is essentially y of x normalized by norm of w. If we mandate that w is, say, unit norm, then y of x gives a sign distance between x and a decision hyperplane. All right. So after we looked at the linear discriminant in some detail and have some intuitions about what either side of this hyperplane is and what distances mean, we can actually ask whether we can generalize, use this to define discriminants for multiple classes, right? So one way to do this is to do what's called one versus all, right? On the left here is two discriminants designed to discriminate class C1 and C2, whereas there are three classes to start with. Oh, okay, C1, C2, and C3 are all the classes. And now we have a line for C1 versus not C1 and C2 versus not C2. So we can see that there is an ambiguous region. So we can see that when it's neither C1 nor C2, we can say this region is R3 or they should be class 3. But what about this green spot, right? It says it's both C1 and C2, and this incurs a contradiction where sort of conceptually the classes should be disjunct, or yeah, they don't overlap. And so a similar sort of dilemma exists if we try and build what's called pairwise discriminants, right? We draw a line for C1 versus C2, and another line for C1 versus C3, and then another line for C2 versus C3. And the green spot is still weird because according to this line over here, it says C3, right? According to this line over here, it says C1. And then according to this line here, it says C2. Right, so exactly, according to 3 different discriminants have three different opinions. Who do you listen to? You can't even sort of say, I listen to the majority, because there is no majority here. Okay, so likely there is a solution to this. What we do is we just define a series of discriminant functions for K classes, and then we essentially take the argmax, right? So the decision class label is we look over all of the discriminant functions that are linear, and then just pick the largest. In fact, this is what's being in use today in neural networks and many other things. So furthermore, the claim is that the decision region of such a discriminant are always singly connected and convex. Being singly connected meaning, right, the region is one piece. I can move from any point to any other point with the pen without having my pen having to leave the paper, right? For example, each of these green blobs on the screen is singly connected, but the combination of them is not. And then convex meaning that if I draw any line between 2 points in the region, the entire line should fit inside the region, right? There is a short proof for that. Basically, if we have XA and XB again in the region for C class K, then basically K y sub kx is the largest for both point A and B, and then we can basically represent any point inside on the line as a linear combination of these 2 points. So any point x hat on the line is lambda xa plus 1 minus lambda xb with lambda in 0 and 1, right? And because the discriminant is linear upstairs, you can each trivially verify that y of k for lambda hat is also maximum among all the other discriminant functions with different k's. So that's nice. So and the picture for 3 classes now look like this. All right. So we talked about linear discriminant functions. This on surface looks no different than the regression function we've been looking at, except just swapping x to 5. But here we can equally just swapping x to 5 and essentially have nonlinear boundaries in the x space. So we've been talking about linear least squares for a week and a half before this. The natural question to ask is whether we can use least squares. So we basically do it as follows. We write out the discriminant function assuming k is binary, 1 and 2. Right? The book presents this part in matrix notation because it wants to be general to multiple k's. So let's, but the equations are essentially the same. So let's just proceed. We're not gonna try and derive this matrix version of it ourselves. And I'm asking you to take me at face value for the next minute. You can go and verify yourself. So in matrix form, when there's more than two classes, it's y of x. And we're also observing the bias term, so it's just y of x equals big matrix W transpose x, right? And we use the familiar square loss function, which is essentially W times x minus the target matrix squared when there's a matrix squared means like matrix product and then taking the trace. And so I leave you to verify that if you like. If you just trust the book, you can say, right, the solution, because we've been working on least squares so much, the solution should be the normal equation. Indeed, so it's essentially x transpose x, or phi transpose phi, inverse times phi transpose. In here, it's x transpose, right? And this whole thing is the pseudo inverse of x, which is denoted here. So you think, okay, great. This is, we have a closed form solution, right? In the rest of this section, you'll see like, okay, closed form solutions are hard to come by. Now that we have one, why aren't we using it? So if we just stare at this, these set of equations and the picture for two-class classification a little bit, right? As we said, the contour lines here are, okay, let me use yellow, are lines, right? So the contours are this way, and W may be pointing at either direction depending on how we label. So W will be like this. And we also say that y of x is sort of, if W is pointing this way, maybe we say that y of x is we can name these contour lines by appropriate scale. Let's say y of x is +1, +2, +3. And then on the other hand side, it's -1, -2, and so on and so forth, right? So the problem comes of what this target variable is, right? In the training data, the target variable is Tij, or is belong to the binary 0 and 1, right? What this means is that if the response variable y is actually +2 or +3, and here, for example, if we're like looking at this point, it's certainly greater than +1, right? And it will be penalized based on the square error function. Meaning in the classification problems, we don't care where the point lies as long as it's on the right, correct side of the discriminant hyperplane. But this intuition is not captured by the least squared loss function. And that's a problem, right? So back to the toy picture we drew a few pages ago, basically, if this loss function does not represent what the problem and the task really want to do, we have a problem. So we see a case of using that picture to help us diagnose what's going on. So what should be the right, right? So what price do we pay then? So the book has a picture to illustrate this. If we use, let's say, a nice function, or the underlying true separating plane should be green. If we use least squares, we find this plane because, look, these bunch of points that are far away from the plane are being penalized where they shouldn't, right? So there is a mismatch between the problem requirement or task and the model specification. So one may say, how do we fix it, right? We can fix it at the loss function stage. Moreover, we can fix it at the model, or basically the definition of f of x, right? I would say the book covers lots of other discriminants. So Fisher discriminant is a historically famous one. We're not going to be able to go into detail here. What it basically does is that assuming there is a red or blue classes, remember that the task of finding a hyperplane is essentially equivalent to projecting the data into a perpendicular dimension W. Basically, imagine we are squashing this two-dimensional space and making all the points living in 1D, and then essentially making a cut in this 1D, right? So why don't we explicitly do this? So here, if we just rotate the hyperplane, or this is the direction of the W vector, then we basically get the different degrees of overlap of the red and blue class. As we saw in the decision series section, overlaps are bad. They incur errors. If there is no overlap or minimal overlap of the red and blue class, it's a good projection direction, right? So one way to do this, we were talking about different objective functions. So Fisher discriminant essentially uses a different objective function, which is the ratio of between class spread versus within class spread. You want the between class spread to be as large as possible, where the within class spread is relatively small. So this is an example of a different objective function that we're not going to hold you responsible in detail, okay? Let's spend maybe the next 5 minutes talking about another interesting discriminant function called the perceptron, right? So the perceptron here fixes, rather than the loss function, it tries to change the model or the functional form of y of x. So the W times phi of x part is the same as linear discriminant. The difference here is f. F is nonlinear, right? So we can introduce ideally arbitrary functional forms. And for the perceptron, which was proposed in the early 60s by Rosenblatt, f function is a step function. We said that while requiring the target to be like penalizing the target for values larger than 1 doesn't make sense. So therefore, let's not penalize them. Let's just make everything that is positive the value 1, right? And this is also an alternative representation other than 0, 1. So it's plus 1 and minus 1. So this is A, this is f of A. Oh, what happened? Okay. Yeah. Right. So. Okay, so we have this f function that solved the problem of the least squares. And we can also define an error function. In here, the target is, okay, where's the writing go? The target is also plus 1 or minus 1. And what we're doing is the error function is the negative of the linear combination of the feature times the target. Basically, if the target is plus 1 and the feature combination is positive, then this term will be large, right? And then if target is minus 1 and the feature linear combination W times phi is positive, the term will be negative. We will want the sign of the W times phi to agree with the target in order for this term to be big, right? And we call it an error function. We want to minimize it. Therefore, there's a negative sign in front. So I think it's just a convention in optimization programs. And I believe a lot of you would have played with the lab where you call fmin con, right? So it does not make sense to develop separate software for maximization and minimization where you can just convert between the two by flipping the sign in front. Therefore, there is a preference in the optimization implementations to minimize functions rather than maximize. In this class, we will sometimes do one, sometimes do the other. But when you code, it's almost always minimize, right? So this makes sense, right? And it does not penalize large absolute values of W transpose phi, which is good. So the way to optimize this error function, or minimize it, is stochastic gradient descent, as we briefly mentioned, which means we go through each data point. We compute the gradient of this error function on that particular data point and update the weights W from one iteration tau to the next iteration tau minus 1, and then we move on to the next point. Turns out if we just stare at 4.54, we can see that the gradient of W is nothing but phi n times t, meaning the sign, this is the input, like we flipped the input vector if Tn is minus 1, and we don't flip the input vector if Tn is plus 1, right? Of course, we only take the gradient step when this particular data point is misclassified. So basically, we shuffle the data set, try to find a misclassified data point, and then take a gradient step using this equation. And then we go to the update the weights, which will give us a new hyperplane, and then we find the next misclassified point using this new hyperplane. So we will see a picture of this in the next page. But what the book says is, so there's nice theoretical results about the perceptron, right? Which is if there exists an exact solution. In other words, if the training data sets is linearly separable, if there is a W to be found that separates the two classes, then the perceptron algorithm is guaranteed to find an exact solution in a finite number of steps, which are all very nice, right? So if they're linearly separable, then perceptron can find it. The bad news is that until convergence is achieved, we don't know when that optimal solution or separable solution will come. In fact, so in essence, and if we found this solution, great. But if we haven't found it yet, we don't know whether it will come. Right. This class will not cover theoretical guarantees of machine learning, but these are some of the statements that will just give you a flavor of it. So here's the pictorial example. The wave vector is indicated in black in here. And the red point here is being misclassified. And this red arrow indicates essentially phi and Tn, basically where the wave vector will move, right? And in fact, so from this first picture, we'll move to the second picture. The new wave vector, this is W1, the W2 is essentially the first wave vector plus the phi and the red arrow here, right? And then it basically proceeds from there. It then finds another red point that's misclassified. It updates the wave vector as the sum of these two again, and we get a new wave vector. And now life seems to be good, right? With this new wave vector W3, we go through the data set trying to find a point that's being misclassified. We couldn't find any. Therefore, we're done. The algorithm has converged. So very nice. So this was proposed in the 60s. It's worth taking sort of a historical view on this. The implementation in the 60s. Right now, you can implement this with maybe 5 lines of Python. And hit run on your laptop and it will do it. Back then, the implementation is through hardware. There are different historical pictures online. It's an impressive machine with many wires, essentially, and resistors and transistors. So the wires are like basically deliberately wired up arbitrarily to show that this machine can learn. Moreover, what's interesting for me was the weights. Each of the weights has a physical implementation, and each weight was implemented using a rotary variable resistor. So basically, it's a resistor with variable resistance, and it's driven by electric motor. It allows the value of the weight to be adjusted automatically by a learning algorithm. So I would say learning weights was a lot more involved back in the 60s than now. It actually involves moving mechanical and electrical parts working jointly together. And it is admirable that the pioneers of machine learning at that stage came up with this conceptually elegant picture of learning to separate two classes with guarantees. And also came up with this physical implementation that actually works. And on the left shows a demo. Basically, this whole system is hooked up to a camera where it's shown digits and pictures, right? It's also worth noting that this is very similar to neural networks. So I think nowadays the press does not give enough credit, or the public does not give enough credit to all the intellectual heritage of how modern machine learning algorithm developed. In other words, the things that are, so there are many things that has happened in the last decade or so, but the core essence, or basically the core algorithm, has remained more or less unchanged. Another historical note was, so Rosenblatt had basically this academic debate with the pioneers of AI, Marvin Minsky. His objection was actually perceptron cannot classify XOR patterns, which you will be able to do in your homework. And Minsky and so on wrote a book, right? And then the book was misinterpreted at the time, showing that the neural network or perceptrons were fatally flawed and couldn't learn much, right? And this has led to a winter of development for related approaches until much later. So this also says that erroneous public perceptions of scientific approach can have detrimental effects for the development of the whole field, right? So that's that. We don't really have time today, so I'll just wrap, and then we'll leave the logistic function and all that interesting stuff until Monday. And I hope people are happy if we leave it today. Is there any questions so far? Nope. If we're all happy, I'm just going to stop the recording to give you a minute or two in case you still want to ask a question. If not, I'll see you on Monday.